Thank you, Sophie. Yes, that's okay. Thanks. I'll get this started. Okay, good afternoon, everybody. Welcome to ICCRG. And this is just a quick overview. We have the IPR policy. Read it very carefully and memorize it every word. I'm going to ask questions later on and see if there are people who have not memorized every word on this slide. It's the IPR rules. It's you should be aware of it. Slightly different for IETF and IETF. I think mainly it's about disclosing any IPR that you may have. This slide is when the IPR is online and the IETF website, you can read it there. The agenda of today, there are 4 talks. David Hayes and talk about congestion for recursive networks. And, I'm not going to read the titles. You're going to see them all anyway. You have them on agendas online. But at the end, we have what is now a 15-minute slot of discussion, and it would be great if that slot would get a little shorter. So there's very wishful thinking here that speakers might even be faster. It's very, 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 very unusual, but we can always hope. Because we have some new ideas. I want to hear some ideas about what ICCRG could be doing that now it currently isn't. And these ideas, the input for making these things come from the one news item which is sitting next to me. That's Jana. We have a new chair.
And I have been told that we are not taking questions on the slide.
Yeah. This is, yeah, indeed. Right, that's already that. So I'll be fast and hand over to the first speaker. Please stay within the time slots. Everybody's got 20 minutes except for the last speaker who didn't ask for more than 15. Let's see. Okay, yes, into pink box. I have that thing. Maybe right. But it could be, I think it controls that thing. No, probably.
Good afternoon. My name's David Hayes from the University of Oslo, and I'll be talking about some work we've been doing on a clean slate internet architecture, and the lessons we are learning from that. It's joint work with Payman and Michael, and it's on the Pristine project. Now, Pristine, who we are, what we're doing. It's a European project. That's a URL you can look up there. We've got quite a number of different partners who are working together on different aspects of this project. And we're working on something called RENA, which is the Recursive Internet Architecture. And it's a clean slate type internet architecture design where hopefully we learn from a lot of the lessons of the present internet and look at how you might design a network having already learned those lessons. And some of the things we're doing is we have some tools, Arena Simulator based on Omnet++. We have a software development kit with C++ so we can build test beds to run networks using this architecture. We're feeding into standards. The Poisson Society only deals with RENA standards, really. And a couple of the things are actually going into ISO and look as if they'll progress there. As well as that, the research, which is what we're the most interested in here, we're looking at, with an architecture such as this, how you handle the scheduling and quality of service, the routing, congestion control, which I'll talk about here, and security aspects as well. Hey, just to look at the differences, everyone in this room is probably very familiar with the left-hand side. That's in its simplest form. It's not what you usually meet because, of course, we have tunnels, we have proxies, we have middle boxes. So that's ideally what it is, but often there are a whole lot of other layers in there, repeated layers and so on, that make it more complicated. A recursive architecture takes the idea that, well, a lot of these layers, some of their functionality is the same. You have addressing at the IP layer, you have it at the transport layer, you have it at the MAC layer, and so on. So all of these repetitive things, rather than have a separate layer for each sort of function, they have a generic layer and then adapt the way those particular layers function. Now, there are two examples, RENA, the one we're working on, and that was John Day's ideas for that. And there's another one that's very closely related, the recursive network architecture, which Joe Touch, I think, was involved with that one. But the general idea is you have a generic layer and you have as many of them or as few of them as you need to get across the network. Now, this example comes from a paper that Payman will be presenting at an ICC symposium in a few weeks' time, where we have a simple scenario, just a two-hop network, what it would look like in the layers with TCP, if you use something like split TCP, and with RENA. That's down the bottom. So with RENA, we have just the two layers above the physical layer in this case, and they look almost the same. They're called diffs for Distributed Interprocess Communication Facility, but it's just a general purpose layer. And in this case, they do congestion control and error control, and also multiplexing and routing. But they're the same they're the same layer. So with this, we had two levels of congestion control. And the results in the paper, they're only just preliminary, just comparing the two architectures, show that there are performance gains to be had from a network that does things that way. Now, just before we go into the congestion control bit, when we talk about congestion control, the types of solvable congestion control, in inverted commas, if you have congestion somewhere, your network can adapt to it. In RENA, that's part of the way it works. It can adapt to the congestion and route traffic along different paths. Okay, you can restrict traffic coming into your part of the network through admission control or policing or something to help with congestion, or, as isn't the case with TCP, the end systems adapt by reducing their rates. In RENA, we're looking at the fact that you can have congestion control under congestion control linked to congestion control. Okay, it has advantages, but when you're stacking and chaining mechanisms like this, of course, how stable is that going to be? And how do you get the signals from wherever the congestion might be to the different entities that are controlling it? We're also, because it's a clean slate architecture, we're looking at some new type of congestion control ideas that are specifically applicable to RENA because of its stacked and chained way it works, but also could be used in the internet as well. This is just an example of a host connected to a server through something like the internet, through a couple of different ISP networks, and how you would layer it in RENA. So they would be called diffs in RENA, but they're just sort of generic layers. And you would probably just have flow control at the bottom red ones, maybe congestion control, maybe not. But at the green, blue, and purple, you would have full error control and congestion control operating. But each layer is roughly the same sort of thing. It only differs in what policies you provide it. So in some sense, that makes it a little like a software-defined network to some respect, because you're defining the function with policies. So say, for example, at what's likely the routing type layer, we have congestion there. Then the question we're looking at is how we get that message of congestion back to where it's needed to go. In RENA, we have, apart from packet loss, we have push back and push up to do with queuing mechanisms. We have packet marking and reflection. We also have control packets that we can send to indicate different things. And in this case, the green layer would be doing congestion control, managing the congestion there. So would the blue layer, and the end host may also be doing congestion control as well. Potentially, that actually can provide much faster responses to congestion and means that the network can have much smaller buffers, so improved latency. Of course, the issue that some of you are probably looking when they see that is, well, how are all of these congestion control things going to interrelate to each other, and is it going to be stable or just oscillate all over the place? And that's what we're looking at as part of this project, and our initial results say that if you manage your feedback properly for your congestion controllers, you actually do get the benefits without the instability. If you don't, then you can get that. Now, the other interesting thing we're looking at is new congestion control mechanisms. Now, this one was inspired by logistic growth in nature. First, just to show that we do go back further than 10 years in this sort of research. This was 1838 when it was first published, and which looks at how in nature populations increase, but there's often a limit to what they can do and how that maps out. In terms of a network, the capacity would be our K there, our limit to our population growth. And the first part of the curve is actually exponential. It's a bit like slow start, except you can manage the rate of the exponential. The difference to something like TCP is when you get close to your capacity, you actually are a lot more careful in getting there. So it's a bit different that way. So with this mechanism, transferring it to a congestion controller, which is working with rates, we calculate our rate based on our last rate. The R parameter there is like a birth rate, or in some sense, how fast you can increase factor. C, the capacity. Then the tricky part, which is why it's hard to do this sort of thing in the internet, but it can be done in a slate type architecture, is we have an estimate of what the other sources over this link are doing, as well as the number of them. Okay, we don't have the exact number, but we have a good enough estimate so we can calculate that and work out how we should change our rate accordingly. Moving on from that, we're looking at predator-prey food chains as inspiration for congestion control, because they have lots of interactions. They're chained and they can be stacked, and the stability of them and the models for them can work. They're enhancements of this one to provide a congestion control mechanism that works well when it's chained to other congestion control mechanisms as well as stacked, and that's an ongoing area of work with us at the moment. Okay, So where are we going? And how does this relate to the current internet? Well, those layers and feeding back congestion control indications, although it doesn't look like the internet, that actually happens in the internet. We have congestion at MAC layers, we have error control not just at TCP, at other layers underneath. They all interact, sometimes badly, in the internet. So this work, although it's on a different architecture, provides insight in how we can manage that better in the internet as well. Coming publications, the one I referred to, we're also nearly finished one with RENA congestion control mechanisms in a data center type architecture dealing with longer flows being sent around. And as I mentioned before, the stability of all this stacking and chaining of congestion control mechanisms and how to do that right. Another highlight is Michael and Payman and Stein have just got 5 years funding to run a project, Ocarina, to optimizations to compel adoption of RENA and take over the world, of course. So thank you.
All right. We're going to do something very unusual before we allow any questions. And that is that well, it's my fault really. I did forget to ask for minute takers, which no harm done yet, but as soon as the first question is issued, we have a problem. So we need a minute taker. Is Aaron here? Because we did make a deal and I wrote my part. Others? Minute takers, come on. Let's say so. That's great, but then we also need a JavaScribe. Jabber, easy job. You just get online and you relay some chat questions. We don't need one. We cannot proceed unless we have one. People are waiting. Come on, come on, come on. Anybody? We do it. We never had it without a JavaScript. I think we have to. Yes, yes, yes. Thank you very much, Mirja. Okay, great. Thanks. Wonderful.
Okay.
Bob, please go.
Bob Briscoe. You'd say that these layered congestion controls exist in the current internet. I've tried to look for things like that. I've not found anything. I mean, yes, there's error correction, there's ARQ, but I don't think there's congestion control anywhere. Like, for instance, ATM frame relay had the ability to do that sort of thing, but when the internet...
You do have it chained with proxies, and potentially sometimes with tunnels, but not to this sort of extent.
But proxies, you could say that's just a redefinition of whether they're an end system or not. Otherwise, it's just TCP congestion control again, or whatever. So it's not really the same.
Well, it is chained because you're communicating end to end, and you've stuck an intermediary to manage two quite distinct
A distributed
paths.
system is made up of things that communicate and transpose the information and send it on again. So it's
Jana Iyengar, on the chaining of congestion control, there is something slightly different than just having TCP connections chained, because the ultimate source of data still is at the far end. All your signaling has to go back all the way to the sender, to the original sender. Are you not able to hear me?
It's sort of a bit blurry.
There's a lot of echo.
It's loud enough, it's just a bit distorted, sorry.
Okay. Yeah, there we go. You can have a conversation here at this mic. So basically, when you have chained congestion control loops, you still have to pass any congestion signals that are deep in the network all the way back to the sender, because your original source of data has to be notified to stop sending somehow.
If it is a source that is congestion controlled rather than a different type of source that may be just admission controlled.
Sure.
So, but yes, that is right, and that's where can be tricky in how you, what congestion information you get so that the source gets everything it needs, which sort of relates to some of the stuff that's happening here when we're trying to get stuff from the MAC layer and congestion happening there, and ECN type signals that propagate all the way back to the sender. And my initial work with modeling some of this stuff has shown that that is actually very important, because if you don't do that, you introduce a lot of instability.
Right, and you have to send it back all the way to the sender. In addition, you have basically you have some sort of coupling between the loops going on.
Probably what I left out in RENA, those different layers, they're not congestion controls of one flow. As you move down the layers, you're controlling an
Different aggregates.
Yeah.
Okay, but if they are operating at the same time scale, you will still have weird interactions between the loops.
If they're operating at the same time scale,
Yes.
you could, yes. But usually they're one loop is
You think of one as the
different to other,
traffic
yeah.
engineering time scale, and the other one is more of a local round trip time.
Yeah.
time
So I'm
scale.
looking at it more from a
Okay.
control fluid theory type analysis, where I'm looking at the control loops and how they interact there.
The coupling is very important. I would point out, and it's important to consider how much latency gets introduced when you have that coupling, because usually when you have these multiple loops, you can introduce instability if you don't have a lot of buffering. But if you have a lot of buffering, you end up getting delay. So there's a trade-off
right.
there.
If you don't feedback properly,
Yeah.
for example, if you just used pushback and not some of the other things,
Yeah.
then you actually introduce more delay and more oscillations, and you need more buffers.
Yeah.
So you have to do it right, or
Yeah.
if you do it right, you have all the benefits, but if you do it wrong, it's worse.
And there are many ways of doing it wrong.
Yeah.
Thank you. Okay, just one note, that standing a little bit further back from the mic helps.
Okay. Any other questions? Any comments? Anything? Okay, well. All right. Thank you. I'll head on to the next speaker, who is Alejandro. Especially warm welcome to a local. Okay, it should be in this box, right? So people can see it in the video. And
Okay, thanks. Good afternoon. I'm honored to be here with you and be allowed to be giving this presentation. This work is about buffer bloat prevention and available capacity fair sharing. First, I'm going to talk a little bit of the origins of the work and what make us work in this. We have been working for a while analyzing the performance of the traffic of the Argentine Chamber of Commerce. In particular, the traffic that goes through the central routing offices of the Chamber. That routes the traffic from the ISPs connected to the exchange points of the Chamber to other ISPs or to the content caches. And
no.
okay, most of these ISPs, members of the chambers, are suffering for severe buffer bloating. We can see at the figures here that the round trip time for the connections, for example, these are connections going from the caches like Akamai or Google caches to the end users in the at the networks of the members, and they are suffering of round trip times of sometimes half a second, sometimes a quarter of a second. You can see there are very high minimum round trip times and larger still average round trip times. Sometimes the round trip times are stable because bottlenecks are exclusive for a single user, and sometimes bottlenecks are shared by many users, and you see this time variation in the round trip times because of the sharing and the overloading that happens at peak hours. So let's see the traffic profiles for regular ISPs that generate these situations. Let's start first with the bottom figures, the figures at the bottom. On the left, we have the traffic that's coming from the caches. In the bottom figures, we see traffic coming from an Akamai cache to regular to users in a regular ISP connected to the chamber. Most of the traffic in red is traffic that is being limited by the congestion control at the sender. The traffic in dark green, that's very little traffic here, that is traffic that is being limited by the data generation rate at the sender. And the traffic in light green here is traffic that we found that was being limited by the flow control at the receivers. We were a little surprised by this because we expected that we were going to find no traffic limited by the receivers. In the figures on top, we see traffic coming from cache to end users. This time we also have this yellow traffic on top that is UDP traffic limited by congestion control at user space, SQUIC. We are not analyzing what's going on with that congestion control, but it is significant in traffic from Google. And on the upstream side, on the right, we see that most traffic is limited by data generation rate at the senders. That is why it's green. But the question for us was, what is the situation with this traffic, light green traffic? What is the performance for those flows? So most of those flows were limited by PCs that were running all operating systems, maybe not using window scaling and having small windows.
Do you want to take questions now or wait till the end?
Yes, you can answer now. You can ask now.
Yes, my name is Stuart Cheshire. I'm just puzzled by in the upstream direction, it's all dark green, which says it's source limited.
Yes, source limited. Because the upstream is requests and acknowledgements. That's why it's dark green, mostly. There are a few uploads to these servers in this traffic.
Oh, I see. So that's a large number of very small flows that don't send enough data to even do anything interesting. Okay.
Yes.
Okay.
So we went and looked inside the average throughput for these connections for the congestion controlled by the senders connections and the flow controlled by the receiver connections, and we found that they were experiencing very similar average throughputs. You can see the top figure for that ISP. They were getting almost the same throughput. For another ISP on the bottom figure, flow control limited flows were having a little smaller throughput, but not very much smaller. So this and these flow control limited connections were not generating buffer bloating, and they were getting almost the same throughput. So there is an opportunity here to use this flow control and to bring the buffer bloat down that we found, and so we started working in an option for this. There are three ways to combat buffer bloating right now. The most common ways is the first two. One way is by using delay-based congestion control or some other congestion control like based on acknowledgement rate measurements that when running on the servers, they get the same throughput without causing this buffer overload. But when they share bottlenecks with regular connections, they start. That's why they're called, they are generally called less than best effort, as Michael have been teaching all of us about all these options. And another way to combat buffer loading that is very popular right now is AQM, queue management. But we found that most of Argentine ISPs were not planning to use it, or maybe they don't have yet studied these options. Maybe they are not even involved in this problem of overloading. But end users were still having problems and feeling the problems. This buffer bloating can be felt by the users when they download, when they surf the web, because usually web pages are composed of many short files, a lot of pictures, and that means a lot of short transactions. And for these short transactions, latency is more important than bandwidth. So we experienced with many options to build this receiver side congestion control, but most of the time we met with situation that when sharing bottlenecks with regular connections, not caring about buffer bloating, the good connections start and the good options got no bandwidth. So we developed a variable for getting feedback from the network that we call XA. Yes, the purpose of this feedback variable is to estimate a share of the shunt available capacity that our connection is getting. And we calculate this variable as the proportional rate response to the in-flight size variations, to in-flight data size variations. Generally, the in-flight data size is limited by the congestion control, a congestion window at the sender, but it can also be limited by the receiver window and the receiver. So any of those options can control. So this algorithm actually can be implemented at the sender or at the receiver. We implemented it at the receiver, but it can be both. So this variable is the variation in rate relative to the variation in data in-flight size multiplied by data size divided by rate. And what can we expect from these measurements? When the in-flight data size is below the bandwidth delay product, then this variable gets a value of 1 when you are below the bandwidth delay product, at 0 when it's above the bandwidth delay product. That's when you're alone at the bottleneck, when your connection is the only connection that is using the bottleneck and is defining the QA and defining the latency. And when there are more connections, then many times and in most situations, this variable is equal to 1 minus the share of the available capacity.
There we go.
We simulated this and measured this, and this is what this variable gets. There is a problem of noise, because other connections, when they vary the size of the number of the packets in the QA, they affect also this variable, and they introduce noise.
Alejandro, a clarification question on the previous slide. What is RA again here?
RA is the connection rate.
And CA?
That is the in-flight data size. That is the number of acknowledged bytes in flight.
So RA is basically CA divided by SR divided by the round trip time? Is RE, how's RE computed? Is RE computed as the in-flight divided by the round trip time, or is it computed in a different manner?
No, array is the rate you measure. The number of bytes you're receiving during a round trip time.
Okay. Yep, okay, thanks.
So you can see the results of XA going down when you're approaching the full capacity and going up to 1 when your share is low. It jumps all the way to 1 when you are below the bandwidth delay product. So we set to construct this congestion control based on this. Our objective was to prevent buffer bloating if possible, but it's not always possible when the queue is already overloaded with packets. There's no way to bring the round trip time down. So we decided in those cases to revert to regular receiver window management. So we established a threshold, and receive window growth was allowed only when the XA variable was above that threshold. And the receive window went down when we detected that the connections were leaving the bottleneck. And these big windows were not needed. The noise induced by other connections variations in their own data sizes, the in-flight data sizes, was an issue. The details for that should be included in another talk because it would be too long. We can see here, I'm going to show you just a few graphs about how these connections evolve. On the left side, we see a regular connection with a cubic sender and a DRS receiver, dynamic right sizing receiver. We can see both connections at the top, how they grow their sequences, byte sequences in the same time. They both get the same rate. Both of them are low at the bottleneck this time, at this test. And we can see the round trip time for the first connection. This should be familiar for all of you who study cubic, how the round trip time grows until it finds the first packet loss, and then it grows again. On the second connection on the right, the round trip time is curved by the receive window that is not allowing the number of unacknowledged bytes to grow much above the bandwidth delay product. That's on the lower figure, on the bottom figure. In the inset there, it shows the in-flight, the number of unacknowledged bytes touching the receive window just above the bandwidth delay product. And what happens when these connections encounter regular connections at the bottleneck? This time we are seeing 4 connections. First one, the purple one, is the one using the Palermo receiver. And the other 3 are using the typical dynamic right sizing congestion receive window adapting. The first connection achieves a low round trip time until the second and third and fourth connection arrives. Then the round trip time starts to grow, and at this point here, the first connection reverts to regular receive window management, and it starts growing its receive window, and the corresponding number of unacknowledged bytes start flowing in the same way as they do between 2 regular connection, 2 regular sender and receivers. we see that the first connection at first loses some capacity, and then it sort of equals the share that is achieved by the second connection. Then when the other connections leave the bottleneck, it reverts back to Palermo receive window adaptation, and the round-trip time comes down again.
Can I just ask what the vertical axis is for the three curves?
I'm sorry?
What is the vertical axis? I can't actually read it. And I just wanted to know what the three things you were plotting were.
Oh, what are the axes?
Yeah.
Okay, on the top figure, the axis is a sequence of the bytes of the connections. The horizontal axis is time. On the middle figure, the vertical axis is round-trip time. And the green line on that figure is the minimum round-trip time, the minimum achievable round-trip time. And on the bottom figure, the vertical axis is the number of unacknowledged bytes for each connection. There you can see
Number of unacknowledged bytes is data outstanding, is it? That's data that's been sent but not acknowledged, yes? So
yes,
that's not C-wind, or is it C-wind? Is it the congestion window, or?
No. These are the number of unacknowledged bytes in flight for each connection.
So it's flight size.
For example,
Yeah.
this yellow line is the boundary delay product, and the number of acknowledged bytes gets just above that product for the first connection, and then goes up when it reverts to regular behavior. This time we are seeing 4 similar connections, all of them use the Palermo receiver, and the axes are the same as in the previous graphs. This time, at first, the round-trip time is curved and it's small, but it starts growing as the connections arrive, but it grows not as fast as it did when the other, when the regular connections were shown on last graph. The first connection number of unacknowledged bytes is kept constant here because it doesn't feel the necessity to grow it because other connections are well behaved, and most of them get a similar share of capacity. So, what does this mean in terms of performance for the end users? This is a test we run at one of the university proxies, at one of the buildings. That was the only proxy for all the traffic of the building. And it was using the modified kernel. We developed this algorithm for the Linux kernel, for Fedora kernels. And we see on the horizontal axis is the download length. We see on the top figure that at small download lengths, it's the same. But when the size of the download file starts growing, the average round-trip times for the downloads gets higher and higher for the red, that is the dynamic right-sizing receiver, and for the Palermo receiver, that is when the proxy had this algorithm enabled, the round-trip time was constant, almost constant. And a price has to be paid for this. It was not free. The average throughput for the connections, for these large connections, went down, but they didn't start. The price was about 25 or 30% for long connections, and depended also on the traffic conditions, but it never went below 30% less. But why would a receiver be willing to pay this price? on the next test, we're going to see, or yes, this is another test that was made this way. On the same proxy, we ran twice each download several times. The first time, the Palermo receiver, the first time the DRS receiver was enabled, and the second time Palermo reception was enabled. And in parallel, there was heavy traffic and large downloads from kernel mirrors. And these downloads that we made for the measurements were major newspaper pages. Those are pages composed of many small files. For example, we can see for this one, this is the Washington Post. The download was only 2.1 megabytes, and those were 33 files. And without with DRS receiver, we got more or less 15 seconds and more or less 10 seconds when using Palermo receiver. For the New Yorker page, the download time went down from 30 to 20 seconds. For Infobae, that's a Buenos Aires newspaper, the download time came down from 40 seconds to less than 20 seconds. And for the Miami Herald, it came down from 11 or 12 seconds to 4 seconds. So this happened because the many files that compose these pages, for example, 100 files for Clarín, 68 for the New Yorker files, 65 for Miami Herald, those were a lot of short transactions whose performances were affected most by latency. And latency came down when the proxy was using the Palermo protocol. So the price paid for the long downloads, this 30% reduction, resulted in 54 approximately percent improvement in the times for regular web surfing. So we think this is a valid option to use or to explore at host proxies connected to ISPs, not focusing on solving this buffer bloat problem. And it's going to improve their experience. It's not a completed work. There are still things that could be explored, different alternatives to find the noise in the measurements. The sender-side version can also be developed. We didn't start that yet, and we are planning to finish the publication for this soon with the details. And for anyone who is interested, we can share with them the sources, or they can contribute with us with the testings, and we'll be very happy to do so. So I'll be happy to answer questions if any of you have any.
We're going to take a remote question first, because there is one. Randall, you're up.
Hi, Randall Jessup, Mozilla. So I'm not too surprised that there's a cost to be paid for this, at least at the high end of transfer sizes. That would tend to imply that people who are expecting to do large transfers may avoid it. The gain at low transfers is very interesting and nice, but perhaps a little surprising as to the magnitude of the gain. My question would be, have you looked, obviously a lot of these we have a lot of small files to transfer, and probably the buffer bloat is affecting the startup of additional HTTP streams for all these small little flows and delaying them. So the question is, have you looked at this with HTTP2? where the things may be a little different. So that's basically it.
Okay, HTTP2 is great for this because you can transform this lot of small transactions in one long download that's going to get your connection adapted to the available capacity. But if you're not using HTTP2, or if you are using any other protocols or other applications, or whatever application that you need small transactions, then you are going to get the gain. You are going to improve performance. But yes, HTTP2 is great, and it also helps with these buffer overflow problems because you switch from focusing on the performance gain from latency to performance gained on bandwidth.
Any other questions in the room now? Okay. Well then, thank you.
Thank you. Good afternoon.
All right, next up is me. I'll press the button also. Try this. Yeah, you're the guinea pig. Yeah, okay. Before I started this, let's see. Cannot be identified, will not be usable. Come on. No. Good. You're good. That's that. No, pretty nice. Did you know that? Oh, nice. That's magic. All right. Thank you. So, okay, this is long time since I presented something here. The work is called, well, now the draft is called TCP and UDP. I think from feedback on the mailing list, I already learned that it's going to have a change of name because the point here is about congestion control mainly. So this is, I'm listed here with underlined because I'm presenting, but also with Shafiqul Islam and Christian Hjort and Chan-Che Yu from Huawei. The motivation here is that we want to be able to combine the congestion controls of multiple flows going from one host to another host. So the same pair of hosts across the internet. And well, we can see that combining these congestion controls rather than letting them fight it out on the network and get some notion of bandwidth, send window as a result, can be very beneficial because they don't, it's only one flow on the network. They don't have this bad interaction. They don't individually increase the queue. You can assign priorities to flows. So there can be a lot of things can work much better. And there are previous methods on that. One very well-known example is the congestion manager, which was pretty hard to implement because you had to take all the congestion control logic out of TCP or SCTP or whatever your protocol is and have that as a separate piece that the protocols essentially go to and say, what is my next window? And so each individual flow will do that. It's a very different programming model. There have been other proposals, and we discussed them in the draft as well. Generally, it can be made easier. Our goal has been to minimize the changes that you need to do to the TCP code. And the problem here is, well, one problem here is that we believe you cannot simply do that with multiple TCP connections because of ECMP. You have equal cost multipath or similar methods in the network that would spread connections across different paths. And then they may not share the same network bottleneck, which may need some way of putting them together. So as a way of trying to address that, the draft that we have submitted makes one concrete proposal on how you can put things into, well, basically encapsulate multiple TCP connections with one UDP5 tuple. On the mailing list, there were other possibilities mentioned. Touch said that this is all not necessary. It's one view. Tom Herbert said that we could use the IPv6 flow label or we could use generic UDP encapsulation. Already I want to ask a question. What do people think about this IPv6 flow label thing? Can I rely on the sender side if I just use multiple connections to the same destination IP address and I give them the same flow label? Are they going to be treated along the same path? I guess that's the semantics of the flow label, but this is like, is that something that routers will really do?
If you've got the same, Gary Fairhurst, so are they TCP flows?
Are they different what?
Are they TCP flows? Do they have port numbers as well?
Yes. So you would have different port numbers, but you would have the same IP addresses and flow label.
Okay, so the UDP guidelines now recommend that we use the flow label as well as the port semantics for load balancing in ECMP. So I'd expect some equipment to use the ports and some equipment to use the flow label currently.
Okay.
The intention was always to use the flow label. This didn't happen. Then people started using ECMP. They now need the flow label, so we're in a transition process. So I don't know whether you get consistent behavior or not. I suspect
All
not.
right. I'm just saying it would be really cool because in that case you don't need to change anything on the receiver side. It's sender side only thing that you do here. So our conclusion from this brief discussion on the mailing list already was to say that we're not going to prescribe one particular method. We're going to describe one, which is the one that I'm going to present later. We can say there can be other possibilities depending on, I don't know what the trade-offs really are. But the point is you probably want to put them together across the same bottleneck. So, because the eventual goal really is to do the coupling of congestion control, I want to present some results here on how we do that. I'll give a high-level view of the algorithm. There is an algorithm in the draft, so if you want to know the details, it really is there. I think it's a bit of a waste of time to go through every line in the algorithm step by step. First of all, this is based on a similar mechanism that we had in the RMCAT working group that was called, which is in a draft called Draft IETF RMCAT coupled CC, where we have essentially a table that keeps track of multiple flows, and there are things going in and things going out. The table contains priorities for every flow, and then it assigns a share of the congestion window that is based on the share of the flow's priority of the total sum of priorities. So that means that numbers used for priorities don't really matter as long, because it's about the sum of these values. You could use values from 1 to 10 or from 0 to 1 or whatever. So this is about how the congestion window share is assigned. And there is some logic that reacts whenever a flow updates its congestion window. Whenever that happens, then we do something, and that something is based on the difference between the previously stored congestion window value and the new value that the flow has just calculated. There are some TCP-specific specialties that we need to do here. So the RMCAP mechanism is a little bit more generic and simpler. But in TCP, because of the states the TCP has, we have to do some specific things here. One thing we did is to say that we only enter slow start if that happens to all flows. Because essentially, as long as we keep X along with general TCP congestion control logic, we shouldn't be in slow start. So if one flow keeps receiving X, but another flow has gone to slow start, we're not going to go to slow start with the overall behavior. And then there's also this notion of a loss event where TCP tries to avoid reacting multiple times during one loss event. We emulated that behavior in RMCAT with using a timer, but in TCP that timer isn't necessary, and really we do have TCP doing this. So this is the fast recovery phase, and we use that phase instead of using a timer. And generally the behavior that we have picked is slightly more conservative than the algorithm in draft IETF RMCAT coupled CC. The result of using it, that is just simulations so far, but we do have real life code of the encapsulation that I'm going to show you, but the congestion control algorithm so far is only in simulations. There are a few bugs here, a few early ones using, in this case, 4 Reno flows across a 10 megabit per second bottleneck with an RTT of 100 milliseconds, and queue length, that's the bandwidth delay product, 83 packets. This is with background traffic using tmix, and this is just to visualize the behavior of the 4 flows. You can see that they fight against each other, have a very strongly fluctuating behavior on the left, and things look essentially like one flow on the right, which also means it's slightly less aggressive. You have a link utilization of 68% on the left, 66% on the right, so that wasn't too bad. But we have a significantly reduced loss and a quite significantly smaller average queue length. Well, it's nothing very surprising about that, right? So we emulate the behavior of one flow as opposed to 4 flows. That shouldn't produce so much queuing, it shouldn't produce so much loss. Prioritization also works very well. That's a graph that, well, we intended to make a theory line as well, but it's always the same with these graphs, that it's so precise that there is no point in putting it in the second line, you wouldn't see it, because we enforce, a priority share on the sender side, so you get precisely the window that you want to have for the flow. So for the priority ratio, for instance, 1.2, you get 0.5. For 1.3, you get 0.3333. For 1.4, you get 0.25. It's just a precise assignment of the priority, which is really just a share of the total. Yeah, and we're working on more results. That's just some early view on the congestion control. We're working on a paper, and we're going to share the results as soon as we can. For the encapsulation, here the idea was to put multiple TCP flows in UDP. So this was heavily inspired by this earlier draft by Stuart Cheshire and another earlier draft that has a similar thing in it. It's almost the same. It suppresses the TCP checksum and urgent pointer field and sets 0 for the urgent flag. We do the same here. It suppresses this TCP source and destination port, need destination ports to be able to fit the whole TCP packet inside the UDP packet without increasing, reducing the MSS. We do that as well, but one difference that we have here is that we actually want to preserve the semantics of the port numbers. So the idea is that a user or like an application running over there would use ports and would see ports, and everything would be just the same as before. Just on the wire, these ports would be encoded in a different way. So we need the ports in some way. And what we did is we made a flow ID, actually the draft calls it the connection ID, that multiplexes, can multiplex up to 32 parallel connections because we just sold the reserve bits. And basically we can do whatever we wish with this header anyway, because it's inside UDP. So we took these bits, assuming nobody is going to want to use them inside TCP, because if you want to play with TCP as an extension inside UDP, then you may probably want to add an option, and we can play whatever as we wish with options. Because we can play so nicely with options also on SYN packets, we use a SYN option and the SYN-ACK option to map ports to this flow ID. So it's an initial message telling the other side what the flow ID is going to be for this port pair. And then both sides know that it's just state on the sender and receiver side. And we can easily put options on SYNs because it's all in UDP. We don't have problems with middle boxes knowing about this protocol because you're the first people to know it exists. Yeah, there is also some more stuff in here. The offset has shifted to a different place, and that can help identifying other protocols, like also distinguishing between that and STUM. That's again is from Stuart's draft, and we just copied that over. So the setup for doing this multiple flow thing here is that we would happy eyeball for TCP in UDP, but we put the mapping, like I said, in the SYN and SYN-ACK. And because we write this code, and the whole idea of this thing is that it's a simple code change in the kernel, we can also put things in the right sequence. So it's essentially you have a normal TCP machinery doing its TCP thing, and just because before it sends out the packet, there is this thing kicks in. If you use the way our code has it, if you use a socket option that says you want to use TCP in UDP, and then it does this remapping of the header to stack it into TCP in UDP. And in doing so, it also sends a UDP encapsulated SYN packet first, and that is followed by a SYN. And because we have to write the server code as well on the server side, we can also say we respond if we can do it. If we can do it, we do it first with the UDP packet. So in this way, we can guarantee that if we don't get the UDP response at first, it's either reordering in the network or the UDP packet was lost, which should greatly reduce the chance of this becoming a problem that you may get a TCP response first, and then you don't know that this TCP in UDP actually works. Because at least in processing in the kernel, we can ensure the correct sequence. The whole thing isn't really a very, very big change in code. What it can give us is that we have a TCP that can very easily evolve. I believe this can be useful as an intermediate experimentation platform as well. You can play with new TCP things, TCP options, and whatever. And using this encapsulation, they would just work whenever UDP works. It has some benefits related to stun. Again, I'm pointing at Stuart's draft, and possible to use other transport protocols too with the same pointer. I would like to say that because the draft about SPUD requirements, it said something about issues with inline SPUD usage, and that turned out to be not a big problem because when we use TCP, then the size of MSS can change anyway. So as you construct a TCP header, depending on the number of options that are there, you will have to calculate the correct size. So as long as this processing of SPUD is known to the TCP code, you just calculate the right size for the payload. There's actually nothing you need to do really. You can consider a SPUD header or whatever header would be before the TCP header, just like a TCP option that comes before TCP. There are some disadvantages. UDP may be blocked or rate limited. QUIC is hopefully going to help here, but really only for ports 80 and 443, whereas the idea here is that we have one well-known port that this whole thing is using, which is probably not going to be 80 and 443. And it does prevent ECMP, but ECMP can be a good thing. That's another issue here, right? It's not necessarily a good idea to always try to prevent that. For now, we have it as a socket option. Maybe it's only interesting to use that when you expect that there will be short flows. That could be a bigger benefit because a short flow can quickly use a larger window that a longer flow has already obtained. So it could be a use case dependent decision. I don't know. That's kind of it's a trade-off in using that. So to conclude, we have finished the implementation of encapsulation for the FreeBSD kernel. This whole thing is in the works, but this code is actually already there and working. The coupled CC code is under development, or a simulation code, and rudimentary code is already being developed for the FreeBSD, so it's not going to be very hard to incorporate that. We're trying to progress pretty fast with that. It's all Huawei sponsored, so thank you to Huawei for this. And questions?
Very Fairhurst again. The use case suggested that the TCP and UDP happy eyeballing would both progress in parallel. And what happens when you get TCP splitters in the network that terminate the TCP or front ends that look into the TCP part? Do you expect that still to be the case? Or does it not matter?
They're not gonna understand the UDP encapsulation.
They don't understand the UDP, so they just pass the UDP straight through.
Yeah.
I guess, and doing whatever they do. So you're hoping, but they could.
Yeah, so if you get the UDP thing back first, you end up bypassing these devices, like the function of the TCP splitting of these devices. For what it's worth, that's what you do, yeah.
The answer is you look at it, yeah, okay.
It's not a trade-off.
Michael Tuxen. You said that you process, on the server side, you process the TCP over UDP packet first. How do you ensure that you get it first? Even if it arrives, on the server side, on the client side, you make sure you send the TCP and UDP packet first. It might be received there, but NICs distribute the packets over multiple cores. So how do you ensure that it's not rerouted by the NIC?
Distribute the packets over multiple cores. So, but I can only speak from the implementation experiments with the FreeBSD kernel that we have. So just the FreeBSD server side, then there wasn't any distribution over multiple cores in our system.
read something from on the packet and distribute it on different things. Yeah, but if it's a UDP packet, it's kind of different than TCP. So
yeah, this is probably a problem. Summary.
Okay.
okay.
All right. Not sure I get it, but yeah.
But I mean, that's why we're here. We're here to solve problems.
Yeah.
So hi, Brian Trammell. Cool stuff. I already said this on the Stack Evo list. I'm just going to say it here again too. I want to basically just do an advertisement for the next session. So you were looking at blocking in UDP and 80 and 443 and not 80 and not 443. We have a talk about that in MapRG, which is in the next session. Can we run the internet over UDP? The spoiler is yes, probably, if we're careful.
Yeah.
Thanks.
Cool.
Jana Iyengar. There are two questions. One of the benefits of doing the congestion manager, for example, I actually don't remember if this was true in the congestion manager or not, but getting shared loss detection and recovery is quite nice when you have a lot of short flows, and that actually contributes to saving a lot of latency. So in this case, you don't seem to have that in here. You seem to have shared congestion control, but not shared, because you can't really easily have that.
What?
You don't have shared loss detection and recovery. Like if you have multiple flows, you can't use data from one connection to kick off a fast retransmit on another connection.
To kick off the fast retransmit.
So think SCTP and streams.
Yeah.
That's very, very helpful.
Yeah, it's a very similar thing. So we got very similar results, I suspect. But I'm not sure I got the question about it. I mean,
there is space here to also do that. You aren't doing it right now, but it's possible to do that.
Yeah.
From a sender, when you're sort of sending all of your traffic through one siphon, you can detect. You know which packets were sent before which packets and which packets were sent after which packets. And if you have the ability to track that time sequencing of packets across multiple flows, you can figure out how to trigger fast retransmissions earlier than you would have otherwise.
I see. Yeah. Okay. Yeah.
That's extremely useful when you have small flows. Going back to like the HTTP or HTTP2 context, where timeouts dominate latency and things of that sort, and things like tail loss probe help a lot. You basically reduce the number of tails you have for loss recovery.
Yeah.
And this goes a long way in reducing latency. So that's a bit of feedback on something else that could be added in there. The second question is the coupling, congestion control coupling. I don't think it requires the framing of UDP, right? You can do this entirely without the framing. And that could be implemented today without having to implement any of the UDP stuff. That's just a comment, and is that something you want to separate out as two separate things?
Yeah, I think you want to separate it out.
Okay.
Because of all the feedback we got also about different ways of encapsulating. So you could be using the flow label, you could be doing generic UDP encapsulation, you could not do anything and not care about it, or maybe just assume that the bottleneck is on the receiver side because the receiver tells you. You could have all kinds of ways of doing it. So I think we want to split it like that, yes. But you also should suggest it, so yes. Okay, I'll put my chair hat on now and say the line is cut after you two, and I'll have to make this short because so Cohen can need some time.
This should be fast. Hi, Matt Sargent. I was wondering if this has any parallels with the multipath TCP effort and sort of the way that they couple congestion control across multiple flows.
It's a little different. It has certain similarities, and in certain ways it's different. It's not the same. They share the goal of trying to be like one TCP, basically, in terms of how the congestion control operates. But it's not like you want to be, this whole resource pooling where you want to, if you go over different paths, you want to be able to shift traffic towards the path that has the least congestion. That is not how this congestion control operates. So it's coupling, but it's slightly different coupling.
Sure. There's also the option, some folks are using this over essentially two single home machines, and they have the option to open multiple subflows across one IP address on machine A and one IP address on machine B. And then you end up in a somewhat similar scenario, I think. It's not always necessarily two interfaces or two unique paths. But
Yeah,
it might
yeah,
be
yeah.
something to see sort of what they're working on versus what you're.
Yeah, I mean, I know about that stuff. It's pretty. It has a lot of similarities. I mean, yeah, if you use it exactly that way, then yeah, I mean, the outcome is probably not very different.
Thanks.
True.
Hi, my name is Miguel Paris. I don't see the point of the coupled congestion control for multiple connections if they don't share the same routing path. I don't see the point.
Okay, yeah, this is why we do the UDP encapsulation.
You are going to explain it? Or?
If they don't share the same path, you don't see the point of coupling them, is what you said. This is why we do the UDP encapsulation. So it's taking multiple TCP connections and putting them under the same 5 tuple, such that routers will send them the same path.
At the point, if I have a connection to him, for example, and another connection from my point to your point.
No, it will be only between the same IP addresses.
The same routing.
Will be the same IP addresses only.
And I don't know.
No, it's about 10 flows between you and him only.
From the same point to
yes,
the same point?
yes.
Yes. Okay. Thank you.
Welcome. Okay. This is your turn. Sorry. I'm not planned out. Okay, let's see if I do slideshow. Better. No, it's a bit bigger. It's bigger. How do I stop it from automatically?
Okay. Good afternoon. My name is Koen de Schepper. This is some work together with Bob, Olga, and Inton. It's about an AQM which can control different two types of congestion controllers. So okay. So maybe first a small recap about proportional integral AQMs. Typically every time interval they calculate a new difference in probability they have to add to a probability that they keep, and that's based on how fast the queue size changes, and that's multiplied by a factor beta. So if the queue size jumps big, then you also need a big compensation for an extra probability. So that's the proportional part. If that has covered all the variations, then of course there is an offset from your target, because in pi you want to have your queue based on a certain target. Then every delta t interval, there is also with an alpha factor calculated how much the error is, and then every time you add a compensation to shift slowly the target or the queue size to the target. Okay. Next slide. So there was some work with in the AQM there is an pi enhanced defined, and some of the enhancements that were defined were good, because instead of a queue length you can estimate the rate, and with that rate which was estimated you could instead of having a target of size you could have a target in delay. And then another important improvement was that based on the probability, the alpha and beta factors should be scaled so that it could be much more stable. So here you see the complete chain where there is a basic pi controller which is enhanced with some parts. The pi controller calculates a probability which is compared by a random variable and makes then drop or mark decisions. Okay, next slide. So an important step is choosing those alpha and beta gain factors. And so the higher alpha and beta factors give a faster response. But of course, to be stable, your phase and gain margins must be above 0, because otherwise they become unstable. And here you see a few curves with different alpha and beta factors. And as you can see, this gain margin, it evolves with a probability in a kind of diagonal way. And the reason for that is the square root in the classic TCP equation, because the rate is proportional to 1 over the square root of the probability. So if your probability gets lower, you actually need a much smaller compensation than when your probability is high. So it's an extra gain that needs to be compensated. So you could put these bars very high and support the lowest probability like this, but then you have a very small alpha and beta factors, which will be very sluggish when your probability or your load is very high. So next slide. The solution that in Pi was used, Pi enhanced, is to scale the alpha and beta factors and to jump based on a probability from one to the other curve. And as you can see in the current Linux implementation, there are 3 of these steps to go up, but to support lower probabilities, you need extra steps, which are also defined in the current Pi draft. So actually these are, you could say, extra internal alpha and beta parameters, which need to be configured on top of your normal basic alpha and beta factors. Maybe next slide. So in the Pi square solution that we proposed, we just remove the square root by actually not controlling P, but a P prime, which is a kind of virtual probability, which is then later squared. So, and the squaring, so you don't need the scaling here, you just use 2 random numbers, which are actually half the resolution, because your P changes in a much smaller space. And you take the maximum of both and compare that with your R square here, this probability. So actually, what happens is that you're controlling the square root of the probability, because it's squared afterwards. So you're actually, your sender becomes proportional to 1 over P prime. So to give you, as the next slide, yeah. So also an extra advantage, of course, is if we use P prime, you saw that already coming, we can also control scalable TCPs, which are proportional to P prime by just skipping the squaring here. Maybe in the next slide. So we did the same derivations which are used in the papers from Misra and Holot, where they use this equation to model TCP Reno on Pi. So we did the same for TCP Reno on Pi square, and the difference is that we just put a square here around P prime, because we're controlling P prime here. And also for scalable TCP, the scalable TCP is just, instead of reducing half a window, because this part is the window divided by 2 in both cases, we have only half a packet. So per mark, instead of halving the window, we only reduce by half a packet, because these terms are actually the queue size at that moment times the probability, which is the rate times the probability. Okay, so as a result, if you look at the next slide, if we compare what is done with the normal Pi, you see that the gain margin is in steps, but if you see how the gain evolves for the P prime, it's a flat line, so you don't need to compensate at all. So you can put your gain, your alpha and beta factors only once, and they are universally applicable for the full range, let's say, of your control. So it simplifies a lot. Also, we saw that you can have a higher gain factor. Okay, next slide. So we did implement this and did a lot of experiments again with this. So it's a Linux implementation. We also have a dual queue option for that. But in this case, in these experiments, we use the single queue, where we use also the rate estimation and the queue delay of the Pi enhanced. There were a lot of, in the implementation, other heuristics which were added there. We just removed them. For now, we don't know exactly why they were used, so we removed them. And also here we implemented compatibility for scalable TCP and normal TCP, classic TCP, where here, based on an ECN classifier, based on if it's non-ECT, it means it's not supporting ECN, it can be dropped. If it's ECT0, it can be marked in the classic way, so with the squared probability. And if it's ECT1, it's supposed to be a scalable TCP, which doesn't need the marking, so which already responds in a scalable way to marking. So also much more. And an example of that is data center TCP. And this, in our experiments, we used here normal cubic. Okay, next slide. So, yeah, maybe quickly, I don't know how much time I still have. So before I presented already some work, so that so this is known that the rate is based on the square root of the probability. For normal Reno, for cubic, it behaves a little bit different, and for data center TCP on a step function, it's a square here. It's based on the square. But if you do that on a instead of on-off behavior on a smooth probability, it behaves data center TCP as a scalable, which doesn't have a square or a square root at all here. And cubic, we use cubic, but we're mostly, cubic is working in the Reno mode, and then it's has this equation, and if you combine them, if you want the rates to be the same, you can have this approximated, and so the probability we apply to data center TCP, we divide by 2 and we square it, and then we apply this to the classic TCP. And that works pretty well. We did some experiments for 5 to 100 milliseconds round trip times, and from 4 to 400 megabytes throughput links. On the next slide. First, I show you some dynamic tests that we did. And here we used Pi with the normal Pi parameters and the normal tuning. So this tuning factor is then based on the probabilities. And this is the Linux implementation, so only with the few steps. Here it's Pi square, which we just have fixed parameters, always a half for alpha, so much bigger, and 10 for beta, also much bigger. And this is one of the experiments which is in the Pi paper, a lightweight control scheme. So this is in figure 8. We read the tests, and the red ones are the Pi control, Pi enhanced, and the blue lines are the Pi square. So for cubic, you see that Pi square works similar, maybe a little bit less overshoot here, because it can have bigger parameters. But for data center TCP, you see that, first of all, Pi is not adapted to it, so it's unstable in between. But because we don't apply the square here and don't do the tuning, and we use the correct parameters for them, first of all, they are very flat because data center TCP is very smooth. Compared to cubic, there is still the big reductions that have to be compensated. And also the overshoot is much lower for data center TCP. Of course, there is underutilization here. So here there are like 10 flows. Here there are 20 added, 20 stop, and 20 stop in this test case. So you see when stopping it goes down, that still is the same. You have to note that this is actually the delay. So the Q delay measured as an average over 1 second. So these peaks in reality are a bit bigger, but much shorter. So that's why they are over 1 second average much shorter. Okay. For the throughput ratio here, we compared also pi and pi square. So here there is throughput. If the line goes up, the throughput is bigger for cubic. If the line goes down, it's bigger for cubic with ECN here. So we used here cubic and cubic with ECN. So these are normal variations because we only test for 250 seconds with 2 flows of 1 of each. This is with pi square. So of course, we assume that under normal conditions, ECN and non-ECN get the same throughput. If we do use data center TCP here and we use pi square with the scalable, so the non-square probability, you see it's also pretty good, comparable with the other ones, except here in this when cubic mode starts to kick in, because the round trip times are very big. So here are the rates from 4 to 400. And here is from 5 milliseconds to 100 milliseconds round trip time in the second line. So you see that cubic becomes a bit more aggressive because it's less round trip time independent. Okay. Next slide. Quickly, if you use the wrong marking, if you would use data center TCP with ECT0, it just shows that you get 10 times more throughput for data center TCP. Also, in the other way, if you would use cubic with ECT1 marking continuously, normal non-ECT cubic would get up to 10 times more throughput. Next slide. These are the queuing delays, and they are all with, these are older results with alpha and beta, the standard pi parameters, so that the gains can be bigger, so that's why the variations here are a bit more sluggish and bigger. So the queue delay here is a target, it's 20 milliseconds. We run again, we compare pi and pi square. The red ones and the purple ones are ECN with cubic, and here the red and the blue, this is cubic with data center TCP running together. So you see the queue sizes are on average around the targets. In pi, it's more the peaks which are limited. Yeah, it's probably because of the parameters who are configured a little bit differently. Also, we need still to do all these tests with the much higher gain parameters to see, but it's a lot of work because it's a lot of experiments. Next slide. So just to tell you that dual queue is actually our deployment goal. So because alpha-res smoothing in the end system and a dual queue with immediate network marking is outperforming any smoothed AQM, such as pi and pi square also, so they smooth in the network. But pi square is useful to control classic queue size. It's simpler and it's automatically tuning, so that's a good thing. And its signal can also be used for scalable TCP, so that's also a big advantage. We also have experiments, so we did here the experiments without dual queue, so there is no ultra low latency. And we did that to show just the impact of one change at a time. Okay, so next slide. Yeah, I think I'm on the conclusion, so I think this is all clear. If there are questions, I think it's maybe more important if we can have some questions.
First, I want to know what happens to the blue sheets. Who has the blue sheets? Anybody's got them and not signed? Okay, they're here. I see. If you haven't signed them, sign them and ask Cohen questions if you wish. But I think I'll formally end it. You can just talk into the mic if you want. Just go on discussing if you want. But I think. Oh yeah, the last session. Sorry, we had a plan to have a discussion about. Oh, you want to say this?
So quick note that we were planning to have a discussion on what ICCRG's roles could be and how we could be more effective. Let's just take that to the list. And if you don't want to share it to the list, feel free to just send an email to either one of us or both of us, and we are happy to take it up from there.
And since Cohen was hoping to get questions, do use the mailing list. You know, mailing list is never ever getting any traffic. So just use the mailing list and ask there.